Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over reaction diagrams again, but I'm going to kind of hit on some points that I may have missed on my other video and kind of clarify a few things regarding reaction diagrams. So let's get into this. We have endothermic and exothermic reactions that we need to be able to identify or be able to understand in a reaction diagram. So what is a reaction diagram? A reaction diagram is a way of showing the energy changes during a reaction. So here is an example. So here I have endothermic and here I have exothermic. Let's start with the endothermic. So here the reaction diagram shows the y-axis as energy and the x-axis as time. And so as time goes, the reaction is starting with reactants. So we start with reactants and we're producing product. And so here we can see that the energy of the reactants is lower than that of the product. So here we have low energy reactants, and you can see that as the reaction goes, the products that are formed have more energy to them. So that's because we can see that the products are higher than the reactants. So more energy here than more energy here. In this case, it's endothermic because in order to go from low energy reactants to high energy products, energy has to be supplied, right? Where does the energy come from for the products to be higher energies? It has to come from the environment. So it's energy is going into the system, into the reaction. So it's absorbing energy from the surroundings. So that's how the product can be higher energy. And so it's endothermic because it's the energy is going into the reaction, into the system. And so a couple of things I want to point out here is that the difference between the energy of the reactant and the top of this hill here, that's called the activation energy. And so this sign here, this double cross sign here, represents what is called the transition state. And the transition state is that state between the molecules where you kind of have the molecules are hitting each other. And during that process of colliding, you have bonds being broken. And at the same time, you have bonds being formed. So you get this, what is called a transition state, where you got both things happening at the same time. So bonds are being broken, and at the same time, bonds are being formed. And so this is happening at this part here. And so this energy is the energy that needs to be overcome in order to form product. So we call that the activation energy. I'll talk more about activation energy in a little bit. So the activation energy is the energy difference between where the reactant energy is here versus the top of the hill where you get your transition state. So this here is the amount of energy needed to overcome that hump and to get the formation of product. Then the other thing I want to point out is the difference between the energy of the reactants and the energy of the product. So right here, this difference here, this is called your delta H, or your change in energy, or change in enthalpy is what it's often called as well. And so this is representing the difference in energy between reactants and products. So here, since the products have a higher energy than the reactants, that means that your delta H, the change in energy, is going to be positive because it's gaining energy. Products have more energy than reactants. Okay, so if I was to recap here or summarize, number one, the endothermic reaction is where energy is gained by the system. So when you go from reactants to products, products end up having more energy than reactants. And so your delta H is calculated by products, the energy of the products, minus reactant. So another way you can think about it is final minus initial. So the final state minus the initial state. So here we have our product energy subtracted or minus the reactant energy. And so since the products are higher energy, you have a big energy here minus a small energy. So big minus small is going to give you a positive value for your delta H. So delta H is positive for endothermic reactions. And so again, just to recap, your activation energy represented by EA, E sub A is your activation energy. That is the energy from the reactants to the peak. So from the reactant energy to the energy at the peak. So this is represents your activation energy represented by E sub A. Okay, let's talk about exothermic. Exothermic is the opposite. So for exothermic, again, we have our reaction diagram here. In the reaction diagram, we're starting with a high energy reactants and we're ending with low energy or lower energy products. So here, the reaction time is going this way, right? So we start the reaction with reactants, and over time, the reactants are converted into products. And if the products are lower in energy, then where did the energy go, right? So we start with high energy reactants, we end up with low energy. So the energy doesn't disappear, it goes somewhere. In this case, it's being released to the surroundings or the environment. So energy here is going out, right, to the surroundings. Or to the environment. Here, energy is going in. So energy is going in, so it's being absorbed. So that's why the products have higher energy. Here, the products have lower energy compared to the reactant. So during the process of going from reactant to product, energy is lost. So energy is released to the environment. So that explains why your products have lower energy. And so again, if we're looking at our activation energy, the activation energy here for the exothermic reaction is again from the energy of the reactants to the top of the peak. So here you can see it's smaller because the reactants are starting at a higher energy than before. But the definition of activation energy is still the same. It's the energy between the reactants level of energy and the peak. And again, at the top of the peak, that's where we have what is called our transition state. And I'll talk about that a little bit more later. And then again, the energy difference between products and reactants is delta H. But here, notice that the reactants are higher in energy than the products, so your delta H is going to be negative, right? Because you start with higher energy and end up with lower energy, so there's a loss of energy and there's the negative sign. So if I recap what I was saying here, in this case, for an exothermic reaction, energy is lost. It's released to the surroundings. This is why we feel hot, right? This would be like a combustion reaction. You put a log on the fire, it starts to burn. That reaction, that combustion that's happening, releases heat. And so that energy is felt by the surroundings. And of course, you are part of the surroundings, so you're going to feel the heat. Here, in this case, energy is being absorbed by the reaction. So if you are part of the surroundings, then you are losing heat. Heat is being absorbed from you to the reaction. This is why cold pack, if you're holding it in your hand, or if you're holding a beaker where an endothermic reaction is occurring, it's going to feel cold. Why? Because it's absorbing heat from your hand. It's absorbing heat from the environment. And so that's why it feels cold. And so in an exothermic reaction, energy is being lost, it's being released to the surroundings. And here again, delta H, the change in energy between your reactants and products, is again equal to the product energy minus the reactant energy. Product final minus the initial. So here, the product energy is going to be small relative to the larger energy of the reactants. And therefore, when you subtract, you should end up with a negative value for delta H. And that's what we have here. And again, the activation energy is the energy from reactants to the peak. And so that is an overview and summary of reaction diagrams. And this is the labeling of a reaction diagram. These are the different parts of reaction diagram that are often talked about. And so I wanted to go over that. And I also wanted to go over endo and exothermic reactions and clarify and show how the reaction diagram for an endothermic reaction versus an exothermic reaction compare and contrast. Okay, so the next thing I want to talk about is to kind of talk more about the activation energy and what that's related to when we're talking about reactions and molecules and what's going on at the molecular level. So stay tuned. Okay, so let's talk about activation energy. So, what is activation energy used for? Well, activation energy is used for a couple of things. First, some of that energy is used to speed up the molecules and have them collide hard enough. So, remember, with the collision theory of reactions, you need molecules to collide. You need atoms and molecules to collide and touch and come together in order to make a reaction. So if they're not going to touch, if they're not coming together, you're not getting a reaction, right? So they have to come together. And not only do they need to come together, but they need to come together hard enough, right? So they need to collide hard enough in order to break bonds and form new bonds. So that's the first thing. The second thing is that not only do they have to collide hard enough, but they have to collide in the right orientation. They have to be positioned in the right way. So, to give you kind of a picture of that, so here I have molecules A and B. So here they're shaped in a certain way. And so in order to get the reaction, in order for them to fit together correctly, you need them to be oriented in the right way. So here, when these collide in this fashion, notice they're not oriented correctly. And so here, no reaction. So these guys could hit as hard as possible, no matter what. They can have enough energy to collide and make a reaction, but because they're not oriented correctly, nothing's going to happen, right? So not only do you have to have them collide with enough strength, enough energy, but they have to collide in the right orientation, so that way the proper bonds that need to be broken are broken and the bonds that need to be formed are formed. So here is the right orientation. And so here's another example of it where, in this case, I'm showing the transition state. So here you can see that if they're going to form in this way, if they're going to collide in this way, then you can't get the transition state that you want, right? You need a bond to form on this end of this molecule with this end of this molecule. So if they're going to collide like this, then that bond is not going to form. So if they're going to collide like this, now you can get that bond to form. And so you get this transition state where you have enough energy such that the bond begins to form, and you get this transition state where you kind of have in between state between reactants and products. And then, so this is at the top of that peak. So we're at the top of the hill. And so now we're at the point where we can actually make the product and we form product. And so again, this double cross up here represents the transition state. Okay, so next, let me show you an example of a real reaction and show you the reaction diagram with the transition state to kind of put this into perspective of a real life example. So stay tuned. Okay, here we go. So here is an example of what I am talking about. So here I have a reaction diagram of a reaction. Here I have OH minus, which is your hydroxide ion. And here I have what is called chloromethane. I have a chlorine atom bonded to a carbon with three other hydrogen bonded to this carbon. So this is referred to as a tetrahedral structure. It looks like a tetrahedron. It's got four sides. And you can see that this is kind of drawn in a three-dimensional way where the solid wedge bond here is coming out of the board. The hashed wedge here that is going into the board. And this is in the plane of the board. So here you've got this back side of the molecule, and then you've got the chlorine pointed straight forward. So you got this space back here, and so this OH molecule, this HO minus, this hydroxide, can then have this space. It can hit the back of the molecule here, and so then it could form a bond between the oxygen and the carbon, but at the same time, it's going to break the bond of between the chlorine atom and the carbon, right? So the first thing I want to point out is that this reaction will not occur unless it's the oxygen facing towards the chlorine. If I flip it, right? If it's a OH here with the minus, if that hydrogen is facing the back of the carbon and collides, that reaction is not going to happen because it's not going to form an oxygen carbon bond because it's the hydrogen atom that's hitting the back of the carbon, right? No reaction. So it's got to be oriented such that the oxygen is facing towards the carbon when it hits. So therefore, orientation matters. Okay, so the orientation has to matter. Also, if the oxygen hits the hydrogen or if the oxygen hits the chlorine, if this is oriented differently, the reaction is not going to happen because the bond here between the oxygen and the carbon is not going to form. They're not going to get close enough. So here, if it's oriented this way, it can come and hit the back of the carbon where you have this space. And if it has enough energy and enough speed to collide hard enough to create the bond and break this bond as well, then it's going to overcome that activation energy. So remember, from here to here is that activation energy. So if it collides, you can form a transition state. So this is what I'm referring to as a transition state. You can see that here, the dotted line represents that the bond is starting to be formed. It's partially formed here. And at the same time, the bond between the carbon and the chlorine is being broken. So it's partially broken. So here we're kind of at an in-between state here. And that's what we call the transition state. And again, we have the double cross here to represent that. And we usually put it in square brackets. So at this point, we're on the top of the hill. We're coming over the barrier, and now it's all downhill. It'll form the two products. So now look at the orientation of the hydrogens. So first hydrogens were pointed this way. This comes in, they straighten out. Now they're in a plane, and then now with this fully formed bond, these are now pushed this way because remember, the electrons in the bonds are repelling each other. So here you're forming these, it's got electrons on it. We got lone pairs on our oxygen. They're coming in. They're going to cause the electrons in the bonds of the hydrogen to be forced this way and repel. And then finally, it's going to kick off the chlorine. We're going to end up with the chloride ion. And now look at the hydrogens are now pushed that way because the electrons in the bond here are pushing and repelling those electrons. So now we have this molecule here. And so that's what a real life example looks like. And so I hope that was helpful. If this video was helpful in any way, if you like this video, then please hit that like button right over there. Also, subscribe to my channel, hit that notification bell so you'll be notified by other videos I put out. And also make sure when you hit that notification bell that you click all so you can be notified by all the videos. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me and have a great day.